Y'all made it today, huh? I thought I was going to be alone. Day after Easter, weather's bad. Should all get rewarded for being here. Why don't we do that? Who wants to start a sign-in sheet? You want to do that?
I'm sorry?
No, just get like someone just start a piece of paper and let's just put your name on it and pass it around. We'll do a free quiz grade. How about that? Sound like a good idea? Right.
Did you see UFC in the weekend, sir?
Pardon?
Did you watch UFC in the weekend by any chance?
I didn't watch it. I heard about it. I did see some of the prelim stuff, but yeah, there was some good stuff. All right, so that's going to go around, and we still have another minute. While we're doing that, I'll put up here what we talked about last time. Okay, yeah, let's get started. So there's a sign-in sheet going around. Make sure you sign in for a free quiz grade. Is it right over here? Yeah. Can you put on the top of that today's date? It's 4/10, I believe. 4/10. And just put underneath that, put quiz. All right, so last time we were talking about exponential functions, right? And we were doing the folding paper thing, and then we were talking about the bacteria, right? So just to remind you, an exponential function looks like this. It's some number raised to the x power. So our variable is up here in the exponent. And then this number right here is called the base. And so our base, whatever number we put here, it must be positive, and it can never be 1. And the examples I gave you were examples that we had talked about where f of x equals 2 to the x. That was one example. So this would be a base 2 exponential function. Another example I gave you with the bacteria was 3 to the x, right? And I believe those are the only two that I had given you, right? So if you go to graph these, the way we did these graphs is we did a t-table, right? We did, whatever the x is, and then like, for example, for this one, 2 to the x, we started plugging in different values, right? We plugged in 0, and we got 1. We plugged in 1, we got 2. We plugged in 2, we got 4. We plugged in 3, we got 8. You can go look back in your notes. You can see that's the table we made, right? So what I'd like to do now is I'd like to show you a new example where this base is actually a number that is positive, but it's smaller than 1. All right? And what we're going to see is that whenever the base is bigger than 1, the graph is going to look like this. And then whenever the base is less than 1, but still positive, our graph's going to look like this. So I'm going to try and convince you that the graph's going to look like this with this next example. All right? So I'll get back to this in a moment. We'll touch on the graphs a little more in a minute. So your next example is going to be this will be our sacrificial page here. It's going to be a problem that I can demonstrate visually. It's going to be a paper, and then what we're going to do is start cutting it in half. Okay, so we're going to cut paper in half. All right, so what I'm going to do is I'm going to make a t-table. I'm going to make, this is going to be the number of cuts, and this is going to be, oops, not number, this is going to be the length. Right? So let's just say, to make this problem easy to understand, let's say that this paper is 1 foot long. It's actually 11 inches, but let's just say this is 1 foot, all right? Just for simplicity's sake. And right now I have not cut this in half yet, right? So with no cuts, how long is it? 1 foot. So I'm going to put 1, all right? And now what I'm going to do is I'm going to take this, I'm going to cut it in half very precisely. All right? So I've now cut it in half. How long is it now? 6 inches, or in terms of feet, that's half a foot now, right? So this is 1 cut, it's half a foot long. With me? Now I'm going to do it again. Cut that in half. Now how long is it? Half of a half, right? So half of a half would be 1/4. So on 2 cuts, I've got 1/4. And now I go again. This is going to start getting hard, right? Very precise, right? So how long is this now? Half of a half, which would be 1/8. 3 cuts, 1/8. Any predictions on the next one? 1/16 would be the next length. So if I cut it again, I would be 1/16. So just like before, I want us to see that what we have here is something that's exponential, where we have a number that keeps getting raised to different powers. Can someone tell me what the number is here that we keep raising to bigger and bigger powers? What is, like, look at this one right here, right? This one was 2 to the x, right? What happened is we kept on raising 2 to bigger powers. 2 to the first power, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th. Over here, what does it look like our number is that we keep raising to higher powers? The 1/2. The 1/2, right? This right here is 1/2 to the 1, right? This one is, what's 1/2 squared? Well, how would you do 1/2 squared if I asked you to multiply 1/2 times 1/2? You just go straight across, wouldn't you? And that'd be 1 times 4? Or, sorry, 1/4. This next one is 1/2 to the 3rd, right? That's 1/2 times 1/2 times 1/2. So we have 3 of them multiplied together. Make sense? 1/2 to the 4th. And then what about this first one? 1/2, what power has to be here to make that a 1? What power do you have to have here to get a 1 here? 1 will give you the original number, right? No? 0. 0. You plug in 0, right? If you plug any number to the 0, is going to be 1. So the thing we have to make the connection on is that this number here is always the exponent, right? This number here is that exponent. 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 The thing that never changes is the 1/2, right? The 1/2 is always the same. It's just the power that changes. Understand? That's what makes this an exponential function. So for this particular problem, right, for this particular problem, the actual exponential function would be 1/2 raised to the x. I asked you to bring your calculators. Hopefully you remembered to bring them. I would like to ask you right now, if I was able to cut this paper in half again, if I were to do it a total of 8 times, can you tell me how long it would be? So what you have to do on your calculator is 1/2 raised to the 8th power. So the way you type that into your calculator is like this. You would do, it depends on your calculator, but you would start with the parenthesis, do 1 divided by 2, close parenthesis, the caret key, 8th power. So you have to first tell the computer calculator that you're going to use the number 1/2, and then raise the whole thing to the 8th. You do not want to do this, although that will actually probably give you the same answer, but this is not the way to type it in, all right? Type it in this way, because this fraction, if I change this number, if I make the fraction different, like if this was like 2/3, then if you do this 2 divided by 3, it would work, but here if you do 2 divided by 3, it wouldn't. All right, so don't do this. Anybody get it? 1 over what? 256. But your calculator is probably going to give you a decimal, right? What is the decimal? 0.0039. Do y'all see what's happening to these numbers? The more cuts I make, right, what? Smaller it gets, right? Will it ever be 0? Theoretically, will it ever be 0? Go half, and then half of that, 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 half of that, forever. And you'll never get to 0. Understand? So if I try and graph this, why do I keep on losing this? Okay. If I try and graph this, does anyone have any questions on how to type this into their calculators? Make sure you bring those. So if I were to try and graph this, here's what it would look like. At 0, where am I? 0, I'm at 1, right? So at 0, I go up 1, and I put a dot here, right? And then when I plug in 1, where am I? 1, I get a half. So 1, I go halfway up like that. And then when I plug in 2, it's half of that. So I go halfway up again, like half of that, right? And when I plug in 3, I get half of that, smaller, and it's just going to keep on happening, right, forever? So this graph is going to look like this, and it's going to approach the x-axis but never get there. So see how I did the dotted line at the end? That's like what we called a horizontal asymptote back when we were doing rational functions, the ones before this. Okay? Questions? So I want to do something else. If there's no questions, I want to do something else. I want you to forget the cutting paper in half for a moment. Just forget it, all right? For that example, we're done. And instead of that, I want us to do this. I want us to sketch the function f of x equals 1/2 to the x. I want us to sketch that function. So remember, what we've been doing in this class, we've learned how to sketch lines, we've learned how to sketch parabolas, we've learned how to sketch polynomials, and then we did rational functions. Those are the ones that sucked, right? The ones before this. Okay, and I told you when we get to exponential that these are going to be probably the easiest out of all of them. And the reason why is because what I'm about to do, all right? There's no like big set of steps or anything. It's just every time I give you an exponential function, I want you to sketch it. What we're going to do is we're going to make a t-table, okay? This is going to be the x, and then this is going to be whatever the function is, 1/2 to the x. And we're just going to use our calculator to get enough points so we can draw the picture. That's it, all right? So we've already done this, right? I mean, I just did this a second ago, right? We plugged in 0, we plugged in 1, 2, 3, right? So that we've already done. What I want us to now do is plug in some negative numbers. So every time we sketch from here on out, when we're sketching exponentials, I want everyone to use the same numbers over here. And here's the numbers I want us to use. I want us to use 0, 1, 2, and 3. Notice I leave some space up here, because I also want you to do -1, -2, and -3. And we're going to plug total here of 7 numbers into the function. We're going to use our calculators. We're going to get 7 answers. We're going to plot those 7 points, and that should be enough for us to draw the picture. So we already did 0, right? We did 0. That gave us, let me do it like this so you can see what goes with what here. When I plugged in 0, I got 1, right? When I plugged in 1, I got a half. Plugged in 2, I got a fourth. Plugged in 3, I got an eighth. All right, so that's just what we already did. But now let's plug in -1. So for this one right here, I'm going to get the answer here. What we're doing is we're taking 1/2 and we're raising it to the -1. Try that on your calculator and see what you get. And I'm going to come over here and I'm going to put -1 here, and then I'm going to have someone tell me what that is. What do you get? You got 2? -2 or 2? Just 2. You should just get 2. Now, let me explain what's happening here without getting too detailed. We have a property in algebra that if you ever have a fraction and you raise it to a negative number, that what you can do is you can flip the fraction over and raise it to the positive number. This is a property of algebra. A fraction raised to a negative number is the same as flipping the fraction and raising it to the positive number. So this right here is the same as take that fraction and flip it. What would you get if you flipped that fraction? 2 over 1, and then raise that to what power? Positive 1, not negative 1. You all see that? And what's 2 divided by 1? 2, and then what's 2 to the first power? Just 2, right? So does that make sense that that's 2? What about this one? This would be 1/2 to the negative 2. Let's try it without a calculator. Flip it, yep, so flip it first, right? It's 2 over 1 squared now. So that becomes positive, but we flip the fraction. 2 over 1 is 2, but then we square it, 2 squared is 4, right? Make sense? What would the next one be? It'd be 8. It'd be 8, exactly. It'd be 8. I'm not showing that one, but you do the same thing, right? 1/2 to the negative 3 is 2 over 1 to the third, which is 2 to the third, which is 8. So coming back to this graph, look at what happens. If I plug in negative 1, where am I at? At negative 1, I'm up 2, right? So I go up 2. Here's 2. So at negative 1, I'm up here at 2. Then at negative 2, I'm at where? 4, so that's way up there, right? Like up here at 4. And then at negative 3, where am I? At 8. I'm off the chart up there, right? I'm like way up there, right? So this graph looks like this. It goes like this, goes like that, and then that takes off, right? That just goes up. And so you've got a graph that looks like this. So to the left, as you go to the left, this thing just keeps growing really fast, right? And as you go to the right, what does it do? It's like that magnet again, right? It gets pulled down towards that magnet. Got it? Okay. Let's see if you understand this. Let's do another one. So I would be done now, okay? I make the table, I plot the points, I'd be done. Let's do another example. Let's sketch f of x equals 2.5 to the x. Let's see what this one looks like. So when you look at that initially, right, you look at it and you say, all right, this is an exponential function. What is the base of this exponential function? What's the base? 2.5, right? It's the number that's down on the bottom. Okay, 2.5. So what I'm going to do is I'm going to make a table. X goes here. I'm going to do 2.5 to the x. And then the numbers I'm going to use here, everyone's going to use the same numbers. Negative 3, negative 2, negative 1, 0, 1, 2, 3. Now here, there's no real easy way to get around using the calculator. You're going to need your calculator to do this. So on the first one, I'm going to take 2.5, raise it to the negative 3. Right, that's what I'm going to do. So please get your calculator, make sure you can do this. You type in 2.5, raise, and then you have to put negative 3 there. So you got to make sure you know how to do that, do the correct keystrokes. On your calculators, there is a difference between, there's a key that I believe has a parenthesis around it, and then there's another key that's just the minus key. This is subtraction, and that's the negative key. So you got to make sure you're using this one to put in the negative 3. Did you get something? Try it? No? What'd you get? Okay, so 0.064. 0.064. Okay. We all good? Try the next one. 2.5 to the negative 2. 0.16. All right. Next one. 2.5 to the negative 1. 0.4. All right. Oh, this one I don't need a calculator for. 2.5 to the 0. What's anything to the 0? 1. I don't need the calculator for the next one either, because I have 2.5 to the first power. And what's any number to the first power? Itself, right? The same number. So this is just 2.5. All right, 2.5 squared, you might need a calculator for. What do you get? 6.25. One more. 2.5 to the third power. Sorry, that's so sloppy. What's that? 15.625, something like that? Okay. All right, so I've made my t-table, right? I've got all my answers, and now I'm going to go draw it. Now, the way I draw this, pay attention to how I draw this, because for this one, remember I had started with the paper, and then after I did the paper, I said, hey, let's act like that's not paper anymore, let's plug negative numbers in. This one, I have the whole table to start, so when I draw my graph, watch what I do. First thing is that I realize I don't have any negative numbers. Do you all notice that whenever you have this exponential function, none of these are negative? Yeah. All your outputs are positive. Okay? That's the first thing to notice. Second thing to notice, what's the biggest value I get out here? What's the largest number I get? 15.6, right? So I've got to make sure that my y-axis goes up to at least 15.6. So what I'm going to do is I'm going to count by fives. 5, 10, 15, 20. And that way I know all my points will fit on my graph. And then going left and right, on graphs, whenever you go, your vertical, your units do not have to match your left and right. So I can still make this 1, 2, and 3, and then -1, -2, -3. So I can change what's called the scale of the axes. One unit here does not have to match one unit here. All right? Let's plot some points now. I always like to start with this one. That one right there, 0, 1. That just means I move up 1 on the y-axis, right? What happens as I move to the right when I plug in 1, 2, and 3? What happens to the graph? Which way does it go? It goes up, right? So when I plug in 1, I'm at 2.5. So that's, I don't know, we're just eyeballing this, right? We're just getting approximately 2.5 is somewhere between 0 and 5. And then when I plug in 2, I'm at 6.25, which is about right, I don't know. Again, just kind of eyeballing it. And then when I'm at 3, I'm at 15.6, so a little bit past 15, somewhere in there. Doesn't have to be perfect, right? And do you all see that this goes like this? This graph is going to grow like that. And what does it do as I start going this way in the negatives? 0.4, 0.16, 0.064. What's happening to those numbers as I move this way? They're getting smaller and smaller, right? Which means they're going to get closer and closer to the x-axis. So I'm not going to be real particular about this. I'm just going to make this go like this. And then I'm going to draw my dotted line. It doesn't touch. Sorry, it looks like it touches there. You know, close enough. So what was the base of this exponential function? Right, that was our base, right? 2.5. And that base is bigger than 1, isn't it? And this base over here, what was the base on this one? This was the function f of x equals 1/2 to the x, right? And the base here is less than 1, right? 1/2 is less than 1. And here, 2.5 is bigger than 1. These graphs look kind of opposite from one another, don't they? This one, as you go to the right, it goes up. And as you go to the left, it flattens out. On this one, as you go to the right, it flattens out. As you go to the left, it goes up. So they're opposite, right? This right here is an example of what's called exponential growth. And you will always have a picture that looks similar to this if a is bigger than 1. So if this base is bigger than 1, I promise you it looks something like this. Not exactly, but it should look similar in the sense that to the right it goes up and to the left it flattens out. Here, this is called exponential decay. And this happens if a is less than 1 but still a positive number. So decay, because as you go to the right, it goes down and just kind of fades away to nothing, all right? So growth and decay come from the idea that, like, if you were to read this like a book from left to right, this grows exponentially, and then if you go from left to right here, this decays exponentially. Good? Do y'all feel like if I gave you a different base, you could use your calculator and fill out this table? Yeah? Okay. All right, so now we need to talk about two very special bases, all right? Our bases can be any number, right? I've shown you when the base is 2, I've shown you when it's 3, I've shown you when it's 1/2, I've shown you when it's 2.5, but there are two bases in particular that are important in the world, all right? In math and in our day-to-day lives, even though you're not aware of it necessarily, there's two specific bases that are used a lot. All right, so the first base that's important two important bases. Right, there's an infinite number of numbers we could have as a base, right? There's an infinite number of numbers, but there's two in particular. The first one is called the natural exponential base. So this number, right, I'm about to put a number here, raised to the x power. Some number I'm about to put here, all right? This number is extremely important. And unfortunately, I can't tell you why it's important, like why it's so special, until you get to Cal 1. And in Cal 1, I would say, hey, we're looking for a function that does this, this, this. Wonder if we can find it, and it turns out that this is the one, all right? So historically, we actually were looking for something, and this turned out to be what we were looking for. So it just naturally is the function that does what we needed something to do. So here's the base. You ready for it? E. Hold on, I thought I said I was going to put a number here. I put a letter. But actually, the letter E stands for number. And don't let this distract you. You've actually seen this before, right? Y'all know what that number is? What's that number? Pi, right? We see this with like circles and stuff. I know in your life you've heard of pi, right? Pi is just a number. Does anyone know approximately what pi is? 3.14, good. 15. And what it actually keeps going forever, which is not that big of a deal. It goes forever. But there's something else about it going forever. It goes forever and it never repeats itself. Like there's no pattern to it at all. It's not like the number, if you take the number 1/3, that's 0.333, and it repeats. Like it just keeps, like even though it goes forever, it just eventually has a pattern to it. And it turns out that not all numbers do that. Not all numbers have a pattern. Some of them go on forever without a pattern. And when that happens, we call these irrational numbers. And so pi is an example of an irrational number. It's a very special irrational number. And so instead of writing 3.1415, we just use this symbol to represent that number. Well, E is exactly the same. E is a special number that acts like this one. E is approximately, does anyone know what E is approximately? Okay, it's 2.718. But again, it goes forever and it never repeats itself, all right? It's just irrational, it just keeps changing, and we actually have never found a pattern to it at all and never will find a pattern to it because it's irrational. So what I'm saying is that this E really just represents a number that's approximately 2.718, all right? So if I were to ask you to graph this, would this be growth or decay? Growth. Why? Because that number is greater than 1, right? So we should expect to see exponential growth. So what I'd like for us to do is I'd like for us to sketch this. All right, let's sketch the e to the x function. And so we're going to do it the way I'm teaching you to do this, and that is we're going to make a table. And here is going to be e raised to the x, and we're going to go -3, -2, -1, 0, 1, 2, and 3. And we're going to plug those in, right? And now we run into a problem, because are you going to use the number 2.718? I mean, you could, right? But your calculator actually has a button for e. It actually has a button there somewhere on there that you can use. So this is a time for you to find that button on your calculator, and if you can't find it, I'll come help you find it. First thing I want you to try and do is do e raised to the -3 power. And let's see if you can get that. And if you need help, I'll come by and help you find your e button. It's probably, most likely, look for a button that looks like this. Look for a button that looks like that. That's an L and that's an N. And then above it, you probably see in a different color, e to the x. Anyone see, or e or something like that? Yes? Okay. What you want to do is, if you hit this button, it's going to do this function, which is actually called the natural log function, which is going to come probably next class. What you want to do to get to that is you have a little shift button. Hit the shift button first, and then you can bring that up. All right, who needs help? Yeah. Yeah, so we're going to round, let's just round like 3 decimal places. So what did you get? 0.049? Anyone else get that? Who needs help getting 0.049? Who needs help? Yes? This is the time. So on your calculator, yeah, so you'll hit, so clear that. Hit the clear right there. So because it's above, right, you have to hit that shift key first. Okay, just hit it. Hit it, and now hit that button. Now, see it says E raised, it's already doing it for you. Now type in -3 and hit enter. Who else? Yes? Oh, okay. Yeah, so do you know how that works?
I do, I just don't know how to make it like...
Do you want to keep it like that, or you want to change it? I have to change the mode. I don't know. I have to look at that. Give me a second. Let me just go around to everyone. Because you're at least getting the answer, right?
Yeah.
You just move the decimal point?
Yeah.
Okay. Okay, for you, where is the... Okay, see it above this? So you'll hit that green one first, then hit that.